Can you hear me? Or you in the room? Okay, I don't need this one, right? Okay, so a few more examples on the solution to differential equations. Here is one. For instance, suppose that I have a differential equation of this type, x dot is equal to minus square root of x over 1 plus t squared. Okay, so first have a look at the differential equation just to classify it, okay? Because this is useful for selecting the solution method. Clearly, this is not. This is a first order linear differential equation. It is non-linear because you see there is a square root of x here. The fact that t is embedded in an expression which is non-linear doesn't affect the linearity of the differential equation. So linear means linear in the variable x and x dot, okay? So here you can have also a very non-linear expression involving t. Also, we can see that this differential equation basically is a separable differential equation, okay? So, of course, x t identically equal to 0 is a solution to the differential equation. Why is that? Remember that a separable differential equation has this structure, x dot is equal to f of t times g of x. Here g of x, the expression that transforms x into something else, is just the square root of x. But if there are values, constant values of x that for which g of x is equal to 0, they are necessarily constant solutions of the differential equation. Here there is one value of x, which is x equal to 0, identically equal to 0, by which this expression is 0, so the right-hand side is 0 for any t, so it is also constant, because it is 0. Its derivative is necessarily constant, so 0 equal to 0, this solution satisfies the differential equation. Once we identify the so-called zeros of the expression g of x, we can divide both sides. In this case, we can separate the variables, okay? In this case, dividing both sides by square root of x, okay? So I write here x dot divided by square root of x is equal to minus 1 over 1 plus t squared, or if you like, x dot times x to the power of minus 1/2 is equal to minus 1 over 1 plus t squared. Now, remember that I have to compute the integral of the first expression, the left-hand side, with integration variable x, okay? And of the right-hand side with the integration variable t. I don't change the name of the variable. I don't call now the new variable, because this in principle is square root of x of t. And I should integrate with respect to t, okay? But x dot dt is du. if I transform the variable, okay? So don't worry about the rigorous substitution method. Just do that. The derivative x dot will become the differential dx, okay? So just consider here the rest of this expression, the integral of x to the power of minus 1/2 dx. Dx is x dot dt. But now you are integrating with respect to x. Is equal to the integral of minus 1 over 1 plus t squared dt. Okay, so here I should increase the exponent by 1 unit, x to the power of 1/2, and divide by 1/2. So 2 square root of x is the result of the left-hand side. Is equal to, what is the integral of minus 1 over 1 plus t squared? It's a power function, not of t, but of 1 plus t. So it's elementary, because the coefficient of t is basically 1. So it is 1 over 1 plus t, okay? It is 1 over 1 plus t plus a constant. So you see the solution to separable differential equations is basically an application, a simple application of integral calculus. You just have to compute integrals. Now, square root of x is equal to 1/2 1 over 1 plus t plus c. And finally, x, which is x of t, so it is a function of t, is equal to 1/4 the square of this times the square of this, times 1 over 1 plus t plus c squared. This is the general solution, okay? It depends on an arbitrary constant. Now suppose that we want x0, x at time 0 equal to 4. Find the particular solution corresponding to the initial condition, or with initial condition, x times 0 equal to 4. Okay? So x at time 0, which is equal by our solution formula to put t equal to 0, is 1 over 4 times 1 plus c squared. 1/4 times 1 plus c squared. This must be equal to 4. Okay? We have to solve for c. This gives a condition on c. So basically 1 plus c squared is equal to 16. And 1 plus c is equal to 4. Okay? And c is equal to 4 minus 1. That is 3. So the particular solution, usually the particular solution is not denoted by just x, but x hat, for instance. Just to denote it, which is 1 among the infinitely many solution curve to the differential equation. X hat of t is equal to, go back into the previous expression, replace c with 3, 1 over 4 times 1 over 1 plus t plus 3 squared. which is, you can also write this as a rational expression, so the ratio between two polynomials, okay? This becomes 3 plus 3t, so it becomes 3 plus 4t. Sorry, 4 plus 3t, so it is equal to 1 over 4. Here you have a fraction like this, 3t, 4 plus 3t divided by 1 plus t squared, okay? So this is the solution curve that satisfies the differential equation first, and second, it satisfies the initial condition by which x at time 0 is equal to 4. You can check this. If t is equal to 0, here you get 4, 1, so the parenthesis has inside 4, squared is 16, divided by 4 is 4. So x at time 0 is actually equal to 4, okay? Now, is there any way to check the solution? Yes, you know that. Just before satisfying the solution, suppose that we want to be more general. Instead of x0 equal to 4, sometimes it is useful to, since c is an arbitrary constant, but it doesn't represent the initial value of the variable, we want to rewrite the equation by making the initial value of the variable appear in the final expression, okay? It's like solving subject to an initial condition, but we don't write x at time 0 equal to 4, but x at time 0 equal to a parameter, which is usually denoted by x0, okay? So let me do that. More generally, with initial condition x at time 0 equal to x0, all the same steps, okay? Here we get 1 over 4, 1 plus c squared equal to x0. So 1 plus c squared is equal to 4x0, okay? 1 plus c is equal to 2 square root of x0. And c is equal to 2 square root of x0 minus 1. Okay? Can you follow the solution steps? Now I want to replace into the solution x hat t in this case is equal to, I have to replace 2 square root of x0 minus 1. So it becomes 1 over 4, this one, plus 2 square root of x0 minus 1. So it is minus 1 plus 2 square root of x0 and this can be rewritten maybe in a different manner because here we have minus 1 minus t, so 1 minus 1 minus t, so it is minus t. Okay, because if you take the same denominator between this one and this one, it becomes minus 1 minus t. Here we have plus 1, so the only surviving quantity in the denominator is minus t divided by 1 plus t plus 2 square root of x0. Let me check if actually x at time 0 is equal to x0. If, sorry, I forgot the square, of course, here. Because in the solution there is squared here. Okay, so squared. Let me check if it works. When t is equal to 0, this becomes 0. Okay, so this becomes 4x0 divided by 4x0. So the initial at t equal to 0, actually I obtain x0. Okay, so this is rewritten in terms of the initial condition in a parametric form. But you see, there is a big difference between the value of the constant, arbitrary constant here, which is a pure mathematical outcome of our exercise, and the way we rewrite the model in terms of the initial value of the variable. So this is useful for applications, of course, okay? And this is just the mathematical output. Now, next step, how can I check the validity of my solution? Of course, we already checked that x at time 0 is equal to x0, but let me check that my expression satisfies the differential equation. So it will be useful to write this in this way. So, check the solution. Okay, so xt, our solution, which is given by, let's rewrite it in this way, 1/4. You can also write it in terms of C, which is even easier, okay? So you can also rewrite this in terms of C. But let me rewrite this in this way. 1/4, 1/1 plus t minus 1 plus 2 square root of x0 squared. Is it minus 1? Right, minus 1, 2 square root of x0 squared. It must satisfy the original differential equation, which is an equation that is a condition that our solution must satisfy, which allows us to find the solution, okay? So it must satisfy x dot, that is its derivative with respect to t, must be equal to, or if you like, divided by xt, must be equal to minus 1 over, let me see okay, divided by square root of xt is equal to minus 1 over 1 plus t squared. Divided by square root of xt must be equal to minus 1 over 1 plus t squared. Now, let me compute first the derivative of my solution with respect to time. It is equal to 2 times 1/4 times 1/1 plus t minus 1 plus 2 square root of x0, right? Times the derivative of the content of the square brackets with respect to t times minus 1 over 1 plus t squared. Okay? On the other hand, if let me just compute the fraction here, the ratio here, okay? If I divide by x the square root of xt, the square root of the solution is this one. Its square root is 1/2 times this without the square, okay? Without the square. Now, here, this becomes 2. So 1/2 disappears. Here I have this one, but this can be simplified away with this one. So my result is just minus 1 over 1 plus t squared, identically for any t, which is precisely what the differential equation required. Okay? was precisely the condition required by our differential equation. So this is a way to check our solution. Okay? I suggest to always do that, because it is a useful exercise, also basically also on derivatives, also on these kind of ratios, which in particular could be the growth rate, but in this case it is just the derivative divided by the square root of the function. These are useful exercises, and in this way I guess you understand much better what you're doing than just solving the exercise. Then you have the final output and what is this? Okay, so now you check that the final outcome corresponds to what required initially by your differential equation. Okay, so this is one example. There is another one which could be interesting, and I could leave it to you as an exercise, in the sense that I give you the text of the exercise and then the solution. So let me solve. Minus x dot, x dot is equal to minus 1 plus t x squared again. The solution with initial condition. We are just applying simple tools in a very friendly manner, but a problem like this, in which you are assigned with an initial, with a differential equation with an initial condition, x at time 0 equal to, for instance, 2. This is called an initial value problem, okay? In the theory of differential equations, this is the statement of an initial value problem. Finding the unique curve satisfying both the differential equation and the initial condition. It is unique because in most cases there is an important theorem of existence and uniqueness of the solution that holds. It is enough, basically it is enough that these functions that appear here are regular functions, that is smooth, common functions, right? There is an initial value problem which relies on a theoretical result which is called existence and uniqueness theorem of the solution. Existence and uniqueness of the solution theorem. So we are sure that there exists only one solution that satisfies the differential equation with a given initial condition, and we have to find it. And remember that the existence and uniqueness theorem holds in many cases in which we are not able to write down analytically the solution, okay? Anyway, we can represent it numerically, and we are sure that there exists a unique solution curve, satisfying the differential equation and passing through that particular point, basically, in the plane, okay? So this is the basic idea. This is called initial value problem. The solution to this is okay. It is xt 2 divided by 2t plus t squared plus 1, and more generally, if you like, with initial condition x0 equal to x0 parameter. The solution is xt is equal to x0 denominator divided by x0 t plus 0.5 t squared, or 1/2 t squared, plus 1. Okay, so this is basically the solution to the exercise. You just have to apply the previous techniques. And remember how to integrate minus x dot over x squared. You have to remember how to integrate minus x dot over x squared. Okay, which is not really difficult. But then, doing all the solution steps, following closely what we did in the previous exercise. Okay, but remember that the most important models are those in which you have x dot is equal to some expression that depends on t times x. Because in this case, it's a matter of finding an unknown functions having a given time growth rate, which is very important in applications. Because in applications, it's useful to model initially, to make assumptions about the time growth rate of a variable, okay? We make assumptions about the time growth rate because it is a percentage change of a variable. And then we put this into our research question, which is the differential equation, and then we solve it, and we find the time paths of the solutions under our assumptions. So the time growth rate example is the most important one. Okay, now I want to show you some additional stuff on differential equations. The first thing I'm going to show you, which takes, let's say, 5 minutes, is just this will not be in the exam, but it is the logistic growth. And the logistic growth is really important in applications to basically environmental applications. Anytime you have some problem in economics or in natural sciences that involves the growth of a population, fish, insects, any other kind of population, and at the same time you have some economic variables and you want to optimize something. So what is really important here is that, remember the first introductory slide on optimizing behavior over an infinite time horizon, okay? So you have something which depends on my decision, for instance, how much to harvest in any given expressed per unit time at any given moment, but there is also a state equation by which my resource evolves due to some natural forces and due to my harvesting, okay? There is a trade-off. And these natural forces often are represented by the logistic growth. Ideally, the logistic growth is similar to the model, so a simple model with the, how did we call it? The second one, with the carrying capacity. We call that model, it's also in your textbook, it's called growth towards an upper limit. But in that case, it was just a linear differential equation. In this case, it is a more sensible specification of the evolution of the natural of the population. Okay, there is again a carrying capacity K, which is basically the maximum level of the population due to exogenous environmental constraints. Okay. And then there is, we model directly the growth rate of the population, x dot over x. And the idea, because many models start from qualitative ideas, like discussing a phenomenon, okay? suppose that, okay, it's reasonable to assume that if there is a large carrying capacity and the population is still a very small size, it grows similar to exponential, okay? Similar, so the growth rate is proportional to the level of the population. But as long as the level of the population approaches the carrying capacity, okay, the growth rate declines. And this simple idea can be written in this way. This equation at the end of the slide, x dot over x is equal to r. R is ideally, this is the growth rate that we would have initially when the level of the population is very low. Suppose it is 0, not 0, slightly above 0, slightly above 0. So this is almost 0, so it is r, okay? In the denominator, we have the carrying capacity. But as long as x increases, this ratio becomes not close to 0, becomes 20% of the carrying capacity, 30%, 70% of the carrying capacity. This reduces, this one, which is a factor that reduces the growth rate, okay? So the idea is this one. If you look at this equation, this one, you see immediately that this equation is, in fact, a separable equation. So in principle, you can solve this equation by separating the variables. And it looks like it is not. Yes, it is a separable equation because you have here x dot divided by x, then divide by this other expression that contains x, okay? You have something that depends on x here and a constant here, okay? So it is a separable equation. And one way to solve it is via separable equation. Another way to solve it is next in the slides. You can have a look at it if you like. It's by a change of variable. It's not part of the program, of course, but it's useful. It's by a change of variable, not so simple as in our previous examples, but it is clear that in that way you can transform the equation into a very simple one. So basically the new variable is takes into account both the level of the population and the carrying capacity. It's a kind of gap between the level of the population and the carrying capacity. If you rewrite the equation in terms of this new variable, okay, look at the variable here. It is this one. Change of variable. U is equal to k over x minus 1. It's the carrying capacity divided by the level of the population minus 1. Okay. So, for instance, if the carrying capacity is 100 and the level of the population is 50, this is 2 minus 1. Okay, so you have something that depends on the gap in percentage terms between the level of the population and the carrying capacity. With this change of variable, it is transformed into a constant growth model. Okay. Anyway, this is not important. What is really important is that you have a look at the solution formula. It is possible either changing the variables or applying separable differential equations theory. It is possible to arrive at the solution. The solution is this one. X of t is equal to the carrying capacity in the denominator divided by 1 plus, this is the arbitrary constant. Next we specify it in terms of the initial level of the population, exponential minus RT, okay? And the shape is like this. You see an exponential-like growth initially, a kind of inflection point, and then something which is smooth, okay? As long as it approaches the carrying capacity level. So this is basically the solution formula. Let me specify A, which is an exercise on applying an initial condition. If I want to rewrite the expression in terms of the initial level of the population, which is really important in applications because you typically have this parameter, so you put this into your solution. If you want to estimate, for instance, these models, x at time 0 is equal to x0. So x at time 0 is equal to x0. X at time 0 is, when this is 0, this becomes 1, k over 1 plus arbitrary constant. K over 1 plus arbitrary constant is equal to x0. You have to solve for the arbitrary constant. So basically it is 1 plus a is equal to k divided by x0, and a is equal to k divided by x0 minus 1. Okay? Or if you like, k minus x0 divided by x0. So this is a, put this, replace a with this expression. Now we have an x0 in the denominator, and there is another denominator. Multiply both numerator and denominator by x0. So this becomes x0, this x0 disappears, and you have the solution here. Okay? This is the solution to our logistic growth equation. For example, if the carrying capacity is 1,000, the initial level of the population is 200, and let's say the growth rate in the absence of constraints is 15% per unit time, this quantity that appears in the solution is, you can also use this formula if you like, this quantity that appears in the solution is k minus x0 divided by x0 is 800 divided by 204. So put 4 here, and this is the solution to your formula, okay? And then, depending on the parameters of the model, you may have different shapes, but in general, what you get is something that initially increases with an exponential-like shape, and then it is leveled off as long as it approaches the upper level. So this is basically the logistic model. This is just to your background. Okay, so to your it's a simple way. There are many ways in which this model is specified. This is the one I like most because it is quite simple to understand here, because what you get here is the carrying capacity in the denominator, and then it is clear that as t increases, this part decreases, and at the end this will disappear, so at the end you will be very close to the carrying capacity eventually, okay? So this is a quite simple, intuitive expression. Now, we will use this, we will use this in an example, maybe already today, without knowing this expression of the solution, but just using qualitatively this one, which is called qualitative analysis or graphical analysis of the differential equations. By the way, this is separable, and it is nonlinear, and it is also autonomous. You see, it is separable, but there is no explicit direct dependence on t. It depends only on the level of the population, so it is autonomous. Okay, this is the logistic growth model. Now, qualitative analysis of nonlinear autonomous differential equations. Okay, so this part is unfortunately, if you look at the syllabus of this course, you see that there is one main textbook, which is the one I follow 90% of the times, and there is another couple of books that are suggested. One of them is this one. By the way, Thanasis Stengos is also one of the co-authors of the book. I'm not sure, he doesn't teach here anymore, but he was teaching to the RESD program up to, I guess, 3 years ago. And he's among the authors. It's the only textbook in which there is a qualitative analysis carried out in a friendly manner, but at the same time not trivial, with many examples. So, I mean, these slides are self-contained, so you don't need to have a look at the textbook, okay? But if you are interested, these slides are taken from that textbook, okay? Which is indicated in the page of the course. Okay, so what is qualitative analysis of nonlinear autonomous differential equations? 90% of the cases, we are not able to solve a differential equation, especially if it is nonlinear. Maybe not 90%. 75% of the times. But we can study its behavior qualitatively and also numerically. But before writing down, let's say, a code to study the behavior of a differential equation, it's much better to understand qualitatively what happens. And then this is a guide to studying our differential equation numerically. Okay? X dot is equal to f of x is the most simple example. I should write g of x here, but anyway, x dot is equal to f of x is the basic scheme of a first order, possibly non-linear, autonomous differential equation. You see, there is no part that depends on t here. It's not f of t times g of x. It is something that depends on x. Okay? We can study qualitatively basically only autonomous equations. If there is also a dependence on t, explicit, direct dependence on t, we cannot study them qualitatively. And the reason is simple. Studying qualitatively means representing x dot as a function of x, because we are assuming that x dot depends only on x. But if there is also a dependence on t, if x is 100, but it is 100 at time 1, or it is 100 at time 5, this changes the evolution of the model, okay? So in this case, we can study qualitatively the differential equation. First, simple question: how can we determine the steady-state solutions, if any? That is, what are the steady-state solutions? The constant solutions of the type x at time t identically equal to x constant, x star. And the answer is very simple. A constant solution, provided it exists, a constant solution to this differential equation is constant. That is, x dot is equal to 0. So we impose x dot equal to 0 here, and we solve f of x equal to 0. The solutions are the levels, not necessarily one, can be multiple steady states, are the levels of the steady state solution. So it's an algebraic equation, f of x equal to 0. And this is the first important point. This is an example. X dot is equal to 1 minus 1 over x squared. Here we don't worry whether we can solve it or not. We just want to study them qualitatively. In principle, it is even useful to study linear equations qualitatively. Okay? It's a different perspective on these equations. Sometimes we don't need the solution formula in order to understand what happens. Okay, so this is f of x. Most of these equations are intended to be for applied models, so x here is positive. Okay? Steady-state solutions need to satisfy f of x equal to 0, that is 1 minus 1 over x squared equal to 0. The only solution is x star equal to 1. Because we exclude both 0 and negative values from the start. So there exists a steady-state solution, a unique steady-state solution, which is x star equal to 1. Now, if our equation is linear, we can immediately know if our steady-state solution is stable or not. Remember, x dot plus ax equal to b. If a is positive, stable. If a is negative, unstable. What about the case of nonlinear equations? Here there is no a, b. It is a nonlinear expression, okay? Okay, in order to understand whether it is stable or unstable, we have to look at the so-called phase diagram, which is a diagram of this function in the space abscissa x, vertical coordinate x dot. Okay, this is the phase diagram. In the phase diagram, we will draw arrows of motion, and all of this is called qualitative analysis of the differential equation. So we have basically to graph f of x in the Cartesian plane. Okay, let me graph, but graphing this function is not difficult. It is the interpretation which is new, because we are graphing the trend as a function of the state. This is what we are representing, drawing. Okay, so if you graph this function f of x 1 minus 1 over x squared, why is this function? Now remember my first class on elementary functions. This is one of the reasons. Okay, elementary functions, you must be able to plot, to draw them immediately. So if I want to draw 1 minus, why is this function? Now remember my first class on elementary functions. This is one of the reasons. Okay, elementary functions, you must be able to plot, to draw them immediately. So if I want to draw 1 minus, okay, let me do that. It's not wasted time, I guess. If you want to draw one minus 1 over x squared, just remember what we learned in the first class about representing functions starting from elementary functions. Remember that x1 over x squared equal to x minus 2 is an elementary power function, okay? And it is like this qualitatively. It's negative minus, so this is 1 over x squared. Minus 1 over x squared is like this, because it's negative. So it's symmetric with respect to the horizontal axis. Minus 1 over x squared. What is the limiting behavior of this? It tends to 0. This one tends to 0. Also, it's negative, it tends to 0. It doesn't cross the horizontal axis. But what about this one plus 1? It will cross the horizontal axis at some point. Okay? Because if this approaches the horizontal axis, and in the limit it is almost 0, if I add 1, this will cross the horizontal axis. So my function, which is the red one, is like this. And if this approaches 0, this will approach 1. Okay? Because it's shifted upwards by 1. And also, what is the intersection point with the horizontal axis? Remember, when you find the intersection point, you write function graph equal to 0, right? When you want to find the intersection point with the axis, the horizontal axis, you write function equal to 0. But function equal to 0 is satisfied for x star, which is 1, steady state, okay? So the point of intersection with the horizontal axis of our f of x is by definition the steady state, because it satisfies f of x equal to 0. So the first nice interpretation of these phase diagrams is that the point of intersection of the phase diagram with the horizontal axis represents the steady state level of the variable. So this is the first main insight from the graph. If you are at the steady state, if the system is here, remember now we are representing x in the horizontal axis, x dot, time derivative of x in the vertical axis. If x is at this level, what is the time derivative? It is 0. So it never moves away from this point. If the system is here, it remains here. Okay. Now, what happens if the system doesn't start at the point x star? If the system starts here, the derivative is 0, and the system remains at the level 1. Okay? Suppose that the system starts, x0 is here. Here. What happens? Look, remember that here we have the time derivative as a function of the level of the variable. The level of the variable is here. What is the time derivative? Where can I read the value of the time derivative? Here. Time derivative is positive. The time derivative positive means that my quantity grows over time. Okay? If it grows over time, the movement, remember that the level of the variable is in the horizontal axis. If it grows over time, the movement is to the right. And these are the arrows of motion. Now, the value of the variable is here. What is at this point the time derivative? It is still positive, even larger than before. Okay? So it grows. Clear? It moves away from the steady state level to the right, to larger values of the variable. But now suppose that the variable starts below its steady state level, for instance, 0.9. What is the value, the value of the time derivative at this point? It is negative. Negative time derivative means the variable xt decreases with t. As time increases, my variable moves to the left because it decreases. Okay? What can we conclude about, okay, this is a steady state, but what can we conclude about its stability? Is that stable? It's not stable, clearly, because if we start we just start slightly on the right, the variable increases, so it moves away from the steady state. We start just on the left, it moves away to the other side. There's no way to start at a different point, except x star, and converge to x star. There's no way. So qualitative analysis suggests that this steady state exists, but it is unstable. It's enough, a small deviation from the steady state is enough to make the system diverge, go away from the steady state in the long run. This is a phase space representation. Phase space means that I check, time doesn't appear here because it is autonomous. I only check the level of the variable and accordingly the time derivative. If I want to represent qualitatively these trajectories, starting from initial condition x0 on the right and x prime 0 on the left, I want to represent it on a time graph with time in the abscissa and the level of the variable in the vertical coordinate. Now remember that x star equal to 1 is here. If I start slightly above this, I have a movement away from the steady state, okay? If I start below, I have a movement away from the steady state. In this particular case, the variable will not become negative because we are restricting to positive levels of the variable, okay? So basically, the solution makes sense up to the point where this remains positive, okay? When it reaches 0, the model is no longer valid, let's say. This is the basic idea. So I hope now it is clear what qualitative analysis can do, because in principle, here we don't have any control over the parameters of a linear equation, right? Because it's not linear, so how can we understand whether the steady state is stable or not? Now, here is another example. I mean, is this clear enough? This is a representation. Here, time doesn't appear. The time, increasing time is intuitively expressed by the arrows of motion, okay? Here is the motion of the variable over time. Here is the motion of the variable over time, but time doesn't appear here. If you want to look more precisely at the time path, you have to represent time in the abscissa at the level of the variable here, but then x0 is above 1, x0 is above 1, and the variable increases over time, and the variable increases over time, okay? X prime 0 is below 1, and the variable decreases over time. So qualitatively, the time paths are like this. And the steady state is clearly not stable. Here is another example. X dot is equal to the exponential of minus 1 over 4x minus 1/2. Okay, so first of all, I want to study the qualitative behavior of the solutions to this differential equation, which is autonomous, depending on the initial condition. I can do that because it is a simple autonomous equation. This f of x here is an almost elementary function. I can represent it and study the behavior. The steady state solution satisfies x dot equal to 0. That is, f of x, which is this one, equal to 0. If I impose exponential minus 1/4 x minus 1/2 equal to 0, this means exponential of minus 1/4 x is equal to 1/2. And this means minus 1/4 x is equal to minus the log of 2. Take logs on both sides. Which means x, change the sign, x is equal to 4 log of 2. That is the log of 16. So x star is equal to 4 log of 2. This is the steady state. Now, how can we represent the phase diagram? It is, again, an elementary function. Was it 1/4 or 1/2? 1/2. 1/2. Okay, so this one, exponential minus 1 over 4th x, is like this. When x is equal, say, to 0, it starts here, basically. Yeah, it goes like this. If we subtract minus 1/2, it is like this. And here, it will approach minus 1/2, the level minus 1/2, okay? And this one will be x star equal to 4 log of 2. starts from 1/2, while this one starts from 1, right? But the hours is the red one. Okay, so this is another example of an elementary function with some qualitative properties, especially reinterpreted in terms of stability. Why is that? Because if you look now at the arrows of motion, and you suppose that you start not, if you start at x star, it is a steady state, the system will remain there forever. But if you start above x star, for instance, x0 is here with a larger value than x star, what happens? Here the derivative, the time derivative is negative. Okay? Go to the graph, go back to the vertical axis, you see a negative level of x dot. Negative derivative means the quantity decreases over time. It decreases over time, and even if you, when you are here, for instance, again, the derivative is negative. It decreases until it reaches the steady state. So if we start with a larger value, the system, the level of the system will decrease until it reaches the steady state. If we start with a smaller value, the opposite happens. Derivative is positive. The level of the variable increases until it reaches the steady state. In this case, clearly, the steady state has a stability property. Can you see the stability property of the steady state? The movement is the opposite. So basically what happens here is that when you are on the right, the derivative is negative. And when you are on the left, the derivative is positive. That is, the function must be decreasing. Okay? Must be a decreasing function, basically. Here, when you start on the right, the derivative is positive, and when you start on the left, the derivative is negative, which means that our graph is increasing. So basically, if it is increasing, let's limit our consideration to monotonic functions, okay? If it is increasing, the steady state will be unstable, if it exists. If it is decreasing, our steady state will be stable. So this is the main insight from the graphical analysis. Okay, so can we represent, at least qualitatively, the possible paths in the time domain, abscissa t, and then xt here. X star, which is 4 log of 2, is, for instance, here. If we start above, which is the case of x0 here, the quantity will decrease until it approaches the steady state, like this. If we start below, it will increase until it approaches the steady state. Okay? So this is a stability represented in the time domain, and this is the stability represented in the phase domain. Phase means state. Okay? Phase means it's a snapshot of the state of the variable. So we don't have the time domain here, we have only the position of our variable, okay? Time domain means that we have the position over time. Okay. So basically, we have seen a simple elementary example of an unstable steady state and a simple example of a stable steady state. By the way, go back to the unstable case. We impose a restriction here on the domain of the variable with positive x, okay? So we only check this set of positive values of x. We are not interested in negative values. Also because at 0 it doesn't exist. So we want a kind of open interval where our differential equation is valid, which is from x on, okay? Larger than x. Is this, okay, this is unstable. This one is defined for any x in principle. So in principle, if we start here with suppose that we can give a meaning also to negative x. If we start here, there is no problem mathematically, that this will increase, okay? Like if it starts here. So basically the domain is the whole real axis. Would you say that this is a globally stable steady state or not? Remember what global stability means. In the limit, each time path will converge to the steady state solution in the limit, independent of the initial condition. For any initial condition, I can select it here, 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 above, below, okay? For any initial condition, in the limit, the system will converge to the steady state solution. Is that true? For any initial condition? Do you think that there are initial conditions that will not lead to convergence to the steady state in the long run? What is your impression? What is your answer? This is a question also for students, online students, of course. Yes, it is globally stable. And the reason why it is globally stable is that this function is decreasing monotonically. It's strictly decreasing monotonically, which means that geometrically, if you start on the left, you will always have x dot positive. So it will increase, whatever the starting point is. And if you start on the right, you will have x dot negative, so it will decrease. So it is globally stable. It is a monotonic f of x, a monotonic phase diagram that has at most a unique steady state, and a monotonic phase diagram decreasing with a unique steady state, of course, has a steady state which is globally stable. So if the phase diagram is monotonically decreasing, strictly decreasing, it has a unique state, and it has a unique steady state, has a steady state which is globally stable. Why? Because there are monotonically decreasing phase diagrams which do not have steady states. Look at this, for instance. This is monotonically decreasing, but if there's an asymptote here, it never intersects the axis, okay? So this doesn't have steady states. But if it is monotonically decreasing and it crosses the x-axis, this steady state is unique and globally stable. It's clear from the graph. So the problem with not global stability is only local stability arises when we have multiple steady states and non-monotonic phase diagrams. Here there is no equation, but it is possibly a cubic equation. Look at what happens. Suppose that your phase diagram is of cubic type. You know, cubic type has generally a minimum and then a maximum, okay, like this. Suppose it is like this. How many steady states? This is x, this is x dot. How many steady states are there? 1, 2, 3. Remember that this is not the only possible case. The steady state could just be 2, could just be 1, for instance, like this. Okay? This is not the only possible case, okay? So we have many cases with nonlinear and non-monotonic phase diagrams. Now what happens here? We can characterize, this is called x star lower, x star upper, and x star for short. 3 steady states. Okay, which are or is stable and which are or is unstable? This one is stable. This one is stable. This one is unstable. Why? What is the intuition? This is non-monotonic, but if I take a sufficiently small region around the steady state, here it is, in this region, it is monotonically decreasing, okay? And also this one, if I take a small region, for instance, like this, here it is monotonically decreasing, close to this steady state. But this one is monotonically increasing. So locally, the behavior of this and this are similar to our first example, today's first example, locally. Sorry, locally, this one, the central one, is similar to our first example, unstable. And this are similar to our second example, locally, stable. And in fact, if you start, for instance, here, you see a positive time derivative. Time derivative is positive, and there is a movement towards a steady state. If you start here, negative time derivative, a movement towards a steady state. Similar here. But here, if you start on the right, derivative is positive. So there is a movement away from the steady state. And this is what is really interesting, because this is unstable. We just call this unstable. Stop. It's not stable. Unless you start here, you will never end up here. Okay? So this is unstable. This is stable, but only locally. This is stable, but only locally. Okay? Locally means that the system will end up here, starting from some set of initial conditions, which is not the whole possible set of initial conditions, okay? Also, this one is locally stable. So this is locally stable. This is locally stable. And this is unstable. Now, the question is, can we, this is locally stable. Locally means not globally, so not for all initial conditions. Can we identify the set of initial conditions that ultimately lead to convergence to this steady state? It is very easy. We can identify it exactly, given the graph. The graph is just on a limited region, but of course this decreases here, continues to decrease, and this continues to increase here, right? So it is decreasing here, then it increases from here to here, the bottom and the top here, and then it decreases again. It has three intersections with the axis. What is the set of initial conditions that lead to convergence to this steady state? Starting from here, can you see the arrow? Starting from here? No, because if we start here, we converge to this, right? Why? Because the derivative here is negative, and it is negative until this point, so it will decrease until here. If we start here at x star, no, because if we start here, we will remain at x star forever. But it is enough that we start slightly above x star, and the final outcome will be x star u. Why? Because in this region, the derivative is always positive. Okay? On the other hand, if we start on the right of x star u, at any point on the right, we will decrease until we reach x star u. So, for this locally stable steady state, the so-called basing of attraction is the open interval from x star to plus infinity. Okay? Any initial condition that lies in this interval, okay, will generate a time path that in the limit goes here. And we assume that f of x now it is defined over 0 plus infinity, okay? It's not defined for negative values Anyway, that's not important. It can also be defined for negative values. What is the basing of attraction of the other steady state? From minus infinity to x star. Is that clear? So we have the two bases of attraction. So what is the time path now? If we want to represent the trajectories in the time domain, there is something new that happens. We have three steady states, so three levels of the variables, x star u, x star lower, this is upper, this is x star lower. X star upper and x star lower are stable, and this is unstable. So if we start on the right of x, above x star, we will have a qualitative behavior like this. But also if we start here, for instance. But if we start below x star, we will have a qualitative behavior like this. Okay? And this is the basing of attraction of XL. And this is up to x star. And this is the basing of attraction of XU. I hope this is, graphically clear enough. So here we have t, and here we have x of t, okay? All the possible, qualitatively we can understand almost everything. Of course, these are only qualitative paths, okay? I'm not sure that this path, I'm not sure at all that this path is like this, or maybe, I don't know, maybe like this. But, okay, but what matters is that it will start and it will converge towards this upper steady state. It can increase in with different types of concavity, convexity, I don't know, because this is just qualitative analysis. Okay. Okay, so the theory of nonlinear differential equations, and this is just a one variable case, but we may have multiple variables, so we have systems of nonlinear differential equations, is in principle one of the most fascinating and new parts of this subject. Okay, many environmental phenomena are of nonlinear type, so it's very promising also for applications, of course. Okay, so this is just a few examples of. Next, we will see an application to two types of problem, which is one problem is kind of dynamic evolution of a population with harvesting, which can be modeled with a simple logistic curve, and the other one is a function that can be interpreted as the phase diagram of a problem of emissions, very simple models that are in the reference textbook, Hoy and others. Okay, but this is just to give you the flavor of the potential applications of this to environmental issues. Okay, so I think that now, let me see if there is more. Okay, this is the case of the logistic one again. And here is the summary of what we did. Okay, so I suggest to stop for 15 minutes and then to continue later and to conclude this part on qualitative analysis. And I hope to be able, let me see, I hope to be able to show you at least one of the examples. And next week we continue next week. Okay. Okay, let's talk for 15 minutes. Okay, thank you. Thank you. So this okay, let's start again. Okay, let's start again. Here. Okay, here is another example which is based on the logistic, very simple type of logistic model. So example 3, x dot is equal to x times 1 minus x. This is probably the most simple numerical example of a logistic curve. We have a carrying capacity which is normalized to 1. And so if you go back to the equation, so k is equal to 1, so this reduces to x times 1 minus x, and also basically x dot over x becomes equal to 1 minus x, and this means that also r is equal to 1, okay? So it is the most simple example, numerical example of a logistic model. And x times 1 minus x can be written as x minus x squared. Okay, so if you go back to the equation, you see that k, the carrying capacity, is equal to 1, and r, the rate, is also equal to 1. Okay, so it is normalized to 100% per unit time, something that doubles every unit of time. Okay, and initially, but then, of course, as x approaches 1, which is the carrying capacity, the rate becomes smaller and smaller, so closer and closer to 0. What are the steady states of this model? So in principle, the population, in an economic model, the population should start from the level, from a positive level, okay? But this is a model which is just a mathematical model here. And so I allow here also negative values for x, just to show you the concept of stability. In the next example, you will see an application to environmental problem, and of course, x will be positive there. There are two steady states in principle. One is 0, x dot equal to 0. And the other one is one is x equal to 0. And the other one is x equal to 1, okay? So x star equal to 0, x double star equal to 1. Why? Because they are the solutions to x times 1 minus x equal to 0. Or they are the zeros of this simple parabola. Why? Okay, there are two because it is a quadratic function. Okay, so you see 0 here, 1 here. Clearly, based on what we already know, 1 is stable locally, while 0 is unstable. Okay? If you start from a positive value, we will have convergence to 1. We start from a value larger than 1, we will have convergence to 1, which is the carrying capacity of the environment of this population. Okay, so it's just you don't need any more comments, because this is already what you know. This is stable, but only locally in principle, because if we start from the left of 0, the movement is towards another direction, okay? But if we start from the right, the movement is towards 1. If we start at 0, the system will remain at 0. Globally stable, already discussed, means that the solutions will converge to the steady state for any initial condition. Only locally stable, or locally stable, means that the solution will converge to the steady state, at least for initial conditions near the steady state, okay? Which is precisely the definition of the intuition we already have about these concepts. In the previous example, the basing of attraction of the locally stable steady state is from 0 to plus infinity. It's clear. It's enough to start slightly on the right of 0 to converge to 1. Any other value will converge to 1. But if we start at 0 or on the left of 0, the behavior will be different. Okay, so the Bayesian of attraction of the stable steady state x star star equal to 1 is the interval from 0 to plus infinity. This also means that if we restrict our analysis to the interval 0 plus infinity, over that interval can be considered globally stable. Okay, this is just mathematical definitions, depending on which domain we consider. The other steady state is unstable. So if you want to represent the time path over time, we have something like this. This is the carrying capacity. If we start from x0, we have the typical logistic behavior. So initially it's close to exponential and then it converges to x star star to 1. In principle, if we start above 1, so beyond the carrying capacity, the population will decline until it reaches the carrying capacity here. But if we start at 0, the system will remain at 0. We start below 0, the system will go exponentially towards negative values. So this is a time path corresponding to this phase diagram. So we have a number of examples already that should clarify, should make things clear. On another point, which is useful to work out, to understand what happens analytically with these models, of course, the qualitative analysis can also be applied to linear equations, linear autonomous equations. In principle, we don't need it, but if we don't want to solve the equation, we can just apply qualitative analysis. This is an example of a linear autonomous equation, x dot equal to minus 1/2 x plus 2. We know how to solve it. And this is our f of x. So let's represent f of x. This is a straight line. Okay? Intercept is equal to 2. The slope is negative. It intersects the x-axis when x is equal to 4. So x equal to 4 is the steady state, which is basically b over a. Minus 1/2 is the constant slope. This is the intercept. The steady state is clearly stable because the straight line is negatively sloped. On the other hand, we know that a, this is x dot plus ax equal to b, a is positive. When a is positive, the steady state is stable. And we know that from the solution formula, in which we have minus a at the exponent, okay? Everything is consistent with what we already know analytically. Since we can solve analytically linear equations, why not, in the case of non-linear equations, why not approximating this non-linear equation with a straight line near the steady state and work analytically on the straight line? This is what linearization does. It's a common method to solve and to derive analytical results on dynamical systems, also of larger dimension, is linearizing dynamical systems near the steady state, which would be, if instead of being linear, this is non-linear, but it has the same steady state, just work on the straight line which is tangent to our graph at the steady state. Okay? We can derive a lot of analytical results in general by doing that, which, since we linearize, they have only local validity. Local validity means near the steady state. when we linearize something which is nonlinear, our results are local. They hold near the particular point where we linearize our functions. Here is another example of a straight line. This is linearization will be the subject of the next slide, but here is another example of a straight line which is positively sloped. It corresponds to the dynamical system x dot minus 1/2 x equal to -1, or x dot is equal to 1/2 x minus 1. This is f of x. The slope here is positive. Okay. On the other hand, a is negative, and we know that the system is unstable. We represent the phase diagram. The steady state is 2, which is b over a, -1 divided by -1/2, 2. Okay. Can also be derived by f of x equal to 0. It is the solution. It is positively sloped, and the steady state is unstable in this case, consistent with theoretical analysis. So phase diagrams are very useful also in the linear case. How does linearization work? Go back to the first example of the first slide today. X dot is equal to 1 minus 1 over x squared. Remember that the graph was this one. The phase diagram was this nonlinear curve. This is the original nonlinear model. We have a steady state, remember, which is unstable, okay? In order to make our idea more rigorous and to build a bridge with the theory, we have to linearize the system near the steady state. Linearizing the system means finding the linear approximation to this curve at the point x equal to 1, okay? Approximate linearly the function near to the point x equal to 1, which means finding the equation of the straight line, which is tangent to this graph, at the point x equal to 1. Okay? So this is a basic tool. We know, I mean, in the midterm exam, there was an exercise on linearizing a two-variable function. So you know how to linearize a one-variable function. Okay, this is the function. We need the value of the function at the point of abscissa 1. But what is the value of the function at the point of abscissa 1? It is 0. Okay? So if you replace 1 here, you get 0. Of course, f of x is 0. Because it is a steady state. We linearize near steady states. The derivative f prime of x is equal to, this is 2 times x to the power of -3. At the point of abscissa 1, this is equal to 2. This is all what we need already. The equation of the tangent is y minus 0, which is f of x star. It is the value of the function at the point near which we want to linearize, is equal to f prime of x star, which is 2, times x minus 1, which is x star. It's very simple. Y is equal to 2x minus 2. It is a straight line, positively sloped, with a negative intercept equal to -2. It is this one. So this is the original nonlinear model. This is the linearized model. It's clear that if we use, instead of using the original model, we imagine that our variable evolves according to this linear model, the qualitative behavior near the steady state will be very similar. Okay? So this can be proven analytically. Okay? So the stability properties are preserved by using the linearized model instead of the original models. Okay? can be proven analytically that the stability properties are, the steady state and the stability properties are preserved. So it is a good, let's say, substitute for the nonlinear model. This is the theory. So we studied the linearized equation, which was x dot is equal to 2x minus 2. Remember that this is if our perspective is on a linear model, this is minus a, okay? So minus a is 2. So a is minus 2. A is negative, the system is unstable. It has the same steady state as the original model. It has the same stability properties as the original model. The only difference is that while the linear model, steady states are globally stable. If we use the linear model as a substitute of a true nonlinear model, we can only conclude that the steady state is locally stable, okay? We can only conclude that it is locally stable because our results hold, by definition, near the steady state locally. Can also be globally stable. In this case, it is. This model is globally stable in this case. But using the linearized model allows us to conclude that the steady state is only locally stable. So this is the basic idea. What would be the solution to the nonlinear model, to the linear model? It would be constant times exponential of 2t plus steady state. Okay. Where the constant is the initial deviation of the variable from the steady state. So basically, instead of working by the set of initial conditions that ultimately lead to convergence to this steady state, it is very easy. We can identify it exactly, given the graph. The graph is just on a limit range. Of course. This continues to decrease, and this continues to increase here, right? So it is decreasing here, then it increases from here to here, the bottom and the top here, and then it decreases again. It has three intersections with the axis. What is the set of initial? Oh, this is a recording of my voice. I was trying to answer a question, but then I recognized that I'm asking a question to myself. Okay, so please turn your microphone off. Once I realized that, I mean, it is monotonic. It not increases and then it decreases again. Okay, so please, okay, very nice. Okay, thank you. And so what is the basic idea here is that, it's funny. Okay, so we can only conclude about local stability. I don't know whether you understand the point. We are not studying the right model. We are studying another model, okay? But the other model has some similarities with the original model, the true model. In particular, if the linear model allows the conclusion that the steady state is globally stable for the linear model, which is not the true model, we can conclude that the true model, we have a stability in the true model, but we can only conclude about local stability, not in general about global stability. But in this case, it is also globally stable if we restrict our analysis to positive values of x, okay? But it depends on the shape. But in general, we cannot conclude about global stability. Look at this case. If we linearize the model here, we get a straight line, which is negatively sloped. For the straight line, for the model described by the straight line, it is globally stable, but it is not the true model. The true model is similar to a straight line here, only near the steady state. Indeed, it is very similar. It is very similar near the steady state to the substitution of the model with a straight line. But if we go away from the steady state, it's totally different. So, while the straight line allows to conclude about global stability, using the straight line as a substitution of the true model allows to conclude only about local stability, but it can be proven that the stability properties, at least locally, are preserved by using straight lines. So the power of straight lines, fortunately. Okay, so this is basically the idea. So here is maybe a summary of the graph here. Okay, this is the linear case, and this is the general case. Okay, B over A, in the linear case, B over A, the steady state is stable if A is positive, and it is unstable if A is negative. What matters for the linearized model is the derivative of f at the steady state. If the derivative of f at the steady state is negative, the steady state is locally stable. If it is positive, it is not stable. So this is the summary. And this is just a repetition of what I already stressed about the local validity of the result. Okay, if you are interested, this is how the linearized system is written in general. And of course, from here you see that f prime of x star is basically minus a, okay? It is our minus a of the linear model. It is f prime of x star. I want to show you a very simple example of logistic growth with harvesting, without using the solution formulas, just looking at the phase diagram. I mean, these models are so simple, it's just a parabola and a straight line, but from these models, we have a lot of insights about the properties of the solution. Okay. So look at this example. Suppose that x of t represent the size of a population of fish at time t. In general, the stock of a renewable resource, okay? Which has some endogenous growth, but also can be exploited with some harvesting rate. This is a simple model. The harvesting rate is a decision variable and is very simple. It is constant, okay? So we assume possible to select only a constant harvesting rate over time, not initially low, then high, constant, okay? So that it reduces to a problem one variable. If K is the carrying capacity of our resource, and R is the growth rate when X is small, in the equation of the logistic growth, this is just the evolution of the size of the population of fish. X stock over X is equal to R times 1 minus stock divided by carrying capacity. And we know that the growth without harvesting is represented by this time path. It starts from x0, initially it grows exponentially, and then it converges to the carrying capacity. And this is the solution formula introduced before. We will not use the solution formula, just to bridge with what we know already. One interesting property one interesting insight is this one. The natural growth, the law of natural growth of the population, if we start with a positive x0 above 0, always will converge in the long run to the carrying capacity, which is a positive amount of stock. So extinction is not a possible final outcome if we start with a positive, even very small, stock of fish, okay? And this can be seen also from the graph. Okay, this is the graph. This is a particular specification. X dot over X is equal to 20%, which is, let's say, the growth rate in the absence of environmental constraints. When the population is very small, for instance, the initial growth rate, times 1 minus stock divided by 100, assuming that 100 is the carrying capacity. Okay? So it's a very simple model. Grows by 20%, but of course, look at this. When the population is already 1/2 of the carrying capacity, this becomes 1/2. So this becomes not 1, but 1/2, 1 minus 1/2. So the growth at that point in time will be not 20%, but 10%, okay? If it is 75% of the carrying capacity, then we will have here 1/4, so the growth will be 5%. So the growth rate declines over time as this approaches 100. If we expand this, we get 1/5 x minus 1 over 500 x squared. This is a parabola, a simple parabola like this. It has two intersection points with the x-axis. One is 0, of course. These models have, logistic models have 0 as intersection. The other one is k, because k, the carrying capacity, is a steady state of the model, because just look at this. This expression is 0 when x is 0, or when x is equal to 100. Because in this case, we have 1 here. 1 minus 1 is 0, okay? So the logistic model has two steady states. One is 0, and one is the carrying capacity. Very simple, 100 in this example. We see from the phase diagram that extinction is not possible due to natural evolution, because if we start with a positive x0, the final outcome will be the carrying capacity. This model can be extended also to levels of the population above the carrying capacity, assuming it's also realistic. Suppose that you introduce a new, exogenously, a new amount of the stock, okay, in a way that the current population exceeds the carrying capacity. Then you will have, since the carrying capacity is a kind of environmental constraint, you will have basically the death rate will be larger than the birth rate, okay, because there is no food basically, and the population will converge back again to the carrying capacity due to this model. So it's also realistic. What is not realistic is the negative values of the population of fish, because the lower bound is 0, of course, okay? So it holds from 0 on. Now, suppose that you introduce a constant harvesting rate. Harvesting rate means amount harvested per unit time. So basically, you have just to modify the original equation by introducing H, which is the harvesting rate, amount harvested per unit time. So x naught is equal to Rx times 1 minus x over k, and then minus H. H is interpreted as a flow, a rate of flow, quantity harvested per unit time. So in principle, what happens to this parabola? You subtract H, subtract a positive quantity. The parabola should be shifted downwards by an amount equal to H, okay? You shift this graph downwards by an amount equal to H. This no longer intersects at 0. This will intersect at a positive value and another positive value, okay? It's clear. It is very convenient not to shift the parabola down, but to shift the axis up, okay, by H. Because the change of coordinates, the new axis, will not be 0, x equal to 0, will be not be y equal to 0, will be y equal to H, okay? This is the new axis. This is the new x-axis in the presence of harvesting. So we don't see the steady states here, 0, 100, but we see the new steady states at this point and this point. So the lower steady state is no longer 0, it is x star lower, which is a positive level of the stock, okay? This is a new steady state. And the upper steady state is no longer the carrying capacity, but it is a value which is smaller than the carrying capacity. So let's say 0 and 100 versus, let's say, 20 and 80, for instance, okay? And this is a big qualitative change of the dynamics of our model. Why? Because look at the qualitative stability properties of these new steady states. Now the arrows of motion are not on this axis, are on the new red axis. What happens here? Suppose that you start at the new steady state x star u. Okay, it is a steady state. We will remain there. You start at the smaller steady state x star L. We will remain there. If we start on the right of x star L, say 21, if the initial population is 21, the population will increase until it reaches the new level, the steady state level 80. So, assuming that this is 20 and this is 80, okay? If we start from a larger level, the population will decrease and reach the level 80 again. But the point is that if the population is 19, now the population will decrease until it reaches the level 0. So in this model, with harvesting, extinction is possible. Okay? So it is possible, and it strongly depends on the harvesting rate, which is the height of this horizontal red line, depending on the depending on the initial condition. So it depends on the harvesting rate in comparison to the initial condition. If this is the new axis and the initial condition is 19, this in the long run leads to extinction. So we have a lot of insights. A new scenario is possible, extinction. This strongly depends on the interaction between the harvesting rate and the current state of the system, which is the current level of the population. Small changes can change a lot in the long run, okay? Because if, suppose that the initial population is 19, but then the harvesting rate goes down, it becomes, let's say, smaller than this one, the axis is smaller. Then the initial condition is no longer in the basing of the extinction scenario. I don't know whether you can see that. It depends on the initial state of the system in comparison with the harvesting rate. And the other insight is that the carrying capacity will never be reached, the natural carrying capacity, but it has been replaced by a new steady state, which is, let's say, the carrying capacity under harvesting, which is smaller than the natural carrying capacity, okay? Which is 80. Let's look at some examples. So here are the insights. The new steady states depend on the harvesting rate. The larger the harvesting rate, the higher is the level of the red new axis. And what happens? The lower steady state increases with age. The upper steady state decreases with age. Is that good news, in your opinion? No. The maximum possible level of the population decreases with the harvesting rate. This is very intuitive. But this is the true, crucial, critical issue. The smaller steady state, which is a threshold between survival and extinction, increases with the harvesting rate. So the larger is the harvesting rate, the larger is the critical threshold between survival and extinction. It's more likely to have extinction as the final outcome with a higher harvesting rate. And all of these insights are clear from a comparison of a parabola with a straight line. So you may think that indeed you need very simple models to understand the qualitative properties of some systems, okay? Anyway, the upper steady state is smaller than the carrying capacity K. If the initial condition x0 is smaller than the lower steady state level, the population evolves towards extinction. And the reason is that the lower steady state is unstable and the upper steady state is stable. Okay, so we learn a lot of things from this simple model. This is stable, this is unstable. When we have an unstable steady state like this, it acts as a sort of threshold between initial conditions leading to some positive outcome and initial conditions leading to some negative outcome. Okay? You can see this And here it is unstable because the phase diagram here is locally increasing, and this is stable because the phase diagram is locally decreasing. So, for instance, regarding this model, we can solve some simple numerical problems, some simple numerical examples. If the harvesting rate is about, say, about 3 per unit time with this model, the equation looks like this. So it is a parabola which has these coefficients. It's very easy to see that we have, if we solve the quadratic equation, we find two steady states. One is 20 and one is 80, as supposed in the previous qualitative. This is 20 and this is 80. Now assume that the current level of the stock of fish is 30. Okay, so you know the model. Except the harvesting rate, which is your decision variable, okay? But you know the model, you know the natural evolution. You have to put some harvesting rate here. Suppose that the initial level of the population is 30. What is the maximum, let's say, affordable harvesting rate? Affordable here just means not leading to extinction in the long run. So you want to know, for instance, what is the maximum harvesting rate we can afford in order not to lead to extinction in the long run. This is a simple problem that is related to this parabola and this straight line. So basically, if you go back to the graph, you know that the initial level of population is somewhere here, okay? Here. The harvesting rate controls the height of this horizontal line. You want to set the harvesting rate in a way that with the new straight line, which will be higher than this one, the system will not converge towards extinction with an initial level of population of 30. So basically, graphically, in words, you can raise this harvesting rate up to the point, the maximum point at which the initial condition lies on the right. The initial condition must not fall on the left, because otherwise this will lead to extinction. So this is basically what we want to do. So mathematically, so this just means that if the initial stock is 30, what is the maximum affordable harvesting rate? You can raise up to the green line, okay? So you want 30 to remain on the right of the new phase, of the new steady state, which will be different from 20, will be larger, okay? So basically you want that the new steady state be 30. This is the reason. So basically, in order to do that, you just write down, you want that the left-hand side here, which is this part of the equation, be larger to h, and this means that h must be smaller than this quantity where you have replaced to x0, 30. So you want h to be smaller than 21/5. Okay, is represented here. If h is smaller than 21/5, so it remains, the new axis remains below the green one, then basically the initial level of the stock will be on the right of the lower steady state. So it will not lead to extinction. So these kinds of graphical insights are, I mean, very simple examples of how to choose a decision variable in order not to have or to have a certain final outcome, okay? Depending on also on the endogenous dynamics of the population. So the population here depends on both The dynamics of the population depends on both your choice, harvesting rate, and the natural evolution. Here, the harvesting rate works as the new level of the horizontal axis. But this changes the two steady states. As long as you remain on the right of the lower steady state, given the current state of the population, this will lead to some positive, desirable final outcome. If you fall on the left, this will lead to extinction. Okay? There is no time to see the next example. We will see it next time. And next time we will conclude also this part, and I will show you how these models, this type of models, dynamic models, work also in discrete time by introducing simple, linear, only linear difference equations, which is the discrete time equivalent of differential equations. And they are also important in economic modeling, so maybe researchers often have to decide initially whether to model in discrete time or continuous time. Choice depends on the type of problem, but they are two acceptable ways to model dynamics. So this is just an example, and I hope that this makes clear the usefulness of this qualitative models. Okay, so thank you, have a nice weekend, and see you next week.
Thank you. Bye.
Bye.
Thank you. Bye.
Bye.